The exclusive NOR gate is similar to the exclusive OR gate. It's similar to the exclusive OR gate. So if you look at the exclusive NOR gate, what we have is the exclusive OR is now inverted. So that's how we're getting exclusive NOR. So if we take a look at what we have here, we have A, B, and Y. So we know that the exclusive OR gate, odd number of ones will give us a 1, and the even number of ones or zeros will give us a 0. So in this case, we look at this. So 0 and 1 and 1 and 0, both those are odd, so those are 1s. But exclusive NOR, because of this inverter, we're inverting that bit. So it's 1, 0, 0, 1. The math symbol is A exclusive NOR, exclusive OR, B. A exclusive OR B is equal to Y and inverted. A exclusive OR B is equal to Y and is inverted. If you have any questions on this, please feel free to touch base with me on it through email or through my office hours or during class. The next part we want to talk about is the universal gate called the NAND. The NAND gate is actually a universal gate because we can actually make any of the ones we just talked about using the NAND gate. For example, the inverter right here, if we make an inverter from the NAND, what we do is we tie one of the inputs of the NAND and we tie it in. Well, if you look at this, we have a 1 here and we put it out, it's a 0, same as the inverter. Look at the AND gate. We take one of the NANDs and then we take one of the NAND that we made into an inverter up here, and now we get into an AND gate. So the NAND gate is considered a universal gate. It is called the universal gate. The next part we want to talk about is gates with multiple inputs. I already started talking to you about this, but remember that a lot of times our gates, any of our logic gates we want, can have multiple inputs into it. So if we have, let's say, an AND gate right here, and we have 3 inputs, well, this is our truth table. Remember, on the left side of the truth table is our inputs, and on our right side is the outputs. So in this case, let's put down all the combinations for this type of gate. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So that should be the whole combination. So we have 0, 1, 2, 3, 4, 5, 6, 7. Yep, that's it. So if we look at that, this is all the combinations that we can get out of this gate. So we want to know what the value of the output of this AND gate. Remember, in an AND gate, everything has to be a high in order to get a 1 out. Well, that's pretty simple and straightforward. So if we look at this, we can have, this will be all the zeros right here, 0, 0, 0, 0, 0, 0, 0, and 1. Because anytime that any of these inputs are 0 and we AND it together, it's going to be a 0. So for example, remember the math on this is A and B and C is equal to Y. So if we have a 0 and a 0 and a 0, well, that's simple enough. That's a 0. Whoops, that's a 0. Even in our case, we have 0 and a 1 and a 0. That's going to be a 0. So remember, in an AND gate, you have to have all highs in order to get it out. What about an OR gate? Well, we could do the same thing for an OR gate. Let's say I have 3 inputs, A, B, and C, and Y out. Well, I do the same thing, A, B, C, and then my Y. So if I have a 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. And you'll get used to that. So if we actually put a 0 in all these, well, we know that. So we know an OR gate, this is an OR gate. Anytime we have a high, a 1 value, then out equals a 1. So all the rest are 1s. All the rest are going to be 1. So what if we have 2 AND gates and an OR gate? Can we have that? Sure can. Truth table is going to be similar. A, B, C. And then we're going to have a Y output. So in this case, we put all our combinations in. And like I said, I'm putting all the combinations I can. And now what we have to do is we have to go through this. So let's say we have a 0. Let's start with 0, 0, 0. So let's say we have a 0, 0, 0 on here. So if I put a 0 right here, a 0 right here, and a 1 right here. So remember, a 0 is equal to ground, and a 1 is equal to 5 volts. So if we put, let's say we ground all these together and we put zeros in. What are we going to get? 0 and a 0? Well, that's going to be a 0. And if we put this one as a 0 and 0, so this is going to be 0, this is going to be a 0, 0 and 0, this is going to be a 0. Now let's say we have a 0, 0, and 1. So it's A, B, C. So 1, this goes 1. So let's do the next one. So 0, 0, 1. So we put a 0, 0, and a 1 right there, because C is 1, high. So now we have a 1 and this is a 0, and that's a 1. That's going to be a 1, because that's an OR gate. 0 and 0 is 0. 0 and 1, 0 and 1 is still going to be a 0. So now let's do a 0, 1, 0. So this one, so we're going to change it out. So 0, 1, 0. Well, that's still going to be a 0. And that's going to still be a 1, but there's still going to be a 0 right here. Let's do the next one. So we have A is 0. And then B and C are 1s. So now what we have here is 0. That's still a 0. And that's going to be a 1. 1 and a 1 is a 1. So 1 and a 0 is going to be a 0 still. So is there any way this is going to be a 1 on the output? Any way this is going to be a 1 on the output? Well, in all honesty, let's see what happens. Well, we know that kids continue on here. A and B, this is still going to be a 0 right here. And this is going to be a 0 because, if you look at this, all we're doing is flipping these 2 bits right here. So that's still going to be a 0. As long as this thing is 0, nothing's going to happen over here. So what we need to do is make sure this one and this one are a 1. So let's see what happens. So we have a 1 and a 1. Well, we now change out to a 1 and a 1. 1 and a 1. And then we have a 0. Whoa, look at that. So they changed. So 1 and a 1 is a 1. Now 1 and a 0 is still a 1, and 1 and a 1 is 1. And there it is. And the last one, because they're all 1s, is a 1. There's the truth table for it. That's the truth table for this logic gate, for this circuit. Can we hook this up in the class and test it? Absolutely. All we have to do is get one chip with dual AND gates and one OR gate, tie up our inputs, and we can actually come up with this. Now, a lot of times what we do when we build a circuit like this in class is in the output. So this is, I'm going to consider this the output right here. So this is just a test point. This is not an inverter, it's just a test point. That's just a test point or a connection point. Let's call this R1. Let's call this 120 ohms. And then what we can do is take that down here to an LED. This means that it is a lighting element and diode, bring that to ground. So what we can do is tie this over here, and then this guy will light up only when this actually appears, 1 and 1 0 and a 1 1 1. And I'll do that testing up in a few minutes. All right, the next section actually discusses how to use an inverter to make a NAND gate. So let's say you have an AND gate chip, but you need a NAND. Well, you can use an inverter. So basically this section right here is just discussing with you how to use the inverter to create some other gates, NAND gates, NOR gates, etc. So for example, if we want to take this OR gate and we want to make it a NOR, all we have to do is add in an inverter right here. Into right here. See how that's an inverter? So that's what a NOR, we talked about this a little bit. let's see, let's say we